How should we update our beliefs when we receive new information? This can be seen as one of the guiding questions for understanding conditional probabilities, and starting with this video, we'll take a deep dive into understanding the process of conditioning. So, if you're struggling with understanding conditional probabilities, conditional expectations, conditioning on sigma-algebras, and so forth, then this series is for you. To recap, in my video about sigma-algebras, we learned that probability theory can be interpreted as an extension to logic in the sense that a statement cannot only be true or false, but rather also be likely or unlikely. In this interpretation, the probability measure summarizes our current state of knowledge, as it is through this measure that we assign probabilities to certain events. But our state of knowledge is usually not static. Rather, every now and then we receive new information such that we need to update our beliefs. That is, we need to update our probability measure. So, how should we do this? Conditional probabilities answer this in a quite scientific and strictly logical way. They simply discard everything that is incompatible with our observations. I'll illustrate this with an example from everyday life. So, assume that you lost your keys. If you do not know anything, your keys could be anywhere on your property. In probabilistic terms, this might be expressed by defining a uniform distribution over your property. But this is not really helpful, as it only tells you that your keys literally could be anywhere with equal probability. So, you might start to think what you actually know additionally. Maybe you did not leave your house today, so the keys actually have to be inside the house and cannot be in the garden. So you can update your probability distribution and assign 0 probability to the garden and full probability to the house. How do you do that? You restrict your probability measure to the area that is compatible with the given information, namely the house, and then you normalize it to get a probability measure again. But your house is still quite a large area to search through, so you go and ask your partner for help. Maybe she tells you that she has seen the keys on a table. So now you know that the keys have to be inside the house and on a table. So every other place does not need to be checked any further, and you can assign 0 probability to them, such that all probability mass is concentrated on the 2 tables inside the house. How do you do that? You take your probability measure and restrict it to the area that is compatible with the given information, that is, the 2 tables inside your house, and then you normalize it to obtain a probability measure again. And as last step, you go and check one of the tables. Either you find the keys directly, or you figure out that they have to be on the other table. In any case, you found your keys. So, what did we do here? How did we incorporate each piece of information? We started with a probability measure, and every time we found some new information, we updated this probability measure to a new one, which is compatible with the information at hand. How did we do this? By restricting and renormalizing. First, restricting to the region that is compatible with the given information, and then renormalizing to have a probability measure again. In probability theory, this process of restricting and renormalizing is called conditioning, and it is exactly this process that is captured in the defining equation for the so-called conditional probability of an event B, given that an event A has happened. And if we compute such a conditional probability for an event B, exactly 2 cases can happen. Either the given information about A does change, or it does not change the probability that we assign to B. If it does change the probability that we assign to B, we have effectively refined our estimates for B with the information given by A. And if it does not change the probability that we assign to B, we call A and B stochastically independent, as knowing A does not change our estimates for B. And I think it's important to pause here for a second and realize that when we are computing conditional probabilities, we are not magically cooking up new probabilities. Rather, we are only discarding everything that is incompatible with the given information at hand. And I think this is important to realize, because then you see that the way of computing conditional probabilities is really just the same as the way in which we could obtain a probability measure from a given finite measure. We simply normalize this finite measure to yield a total mass of 1. And it is actually also exactly the same as when we compute a quote-unquote traditional probability, just that you do not see it directly, as everything is already normalized. Why do I think this is important? Because it shows most clearly that two events A and B are stochastically independent if the relative mass of B in A is the same as the relative mass of B in omega. Nothing more, nothing less. So, to summarize, the conditional probability tells us how to update our beliefs after receiving new information, namely by restricting and renormalizing. And stochastic independence is the special case in which this update changes nothing. With that being said, I hope you enjoyed the video and you could learn something from it, and as always, thanks for watching.